So good morning, everyone. So we have here today Naila Sebastián Esandi, who is currently a PhD candidate at ENSAE Paris, Institut Polytechnique de Paris, where she's part of the FairPlay team, a joint research team involving ENSAE, INRIA, and Criteo. Yeah? Naila is also an ELLIS PhD student, supervised by Vianney Perchet and at ENSAE, and co-supervised by Gergely Neu at Universidad Pompeu Fabra. Yeah? Her doctoral research focuses on zero-shot reinforcement learning, a very active and challenging area within machine learning. Before starting her PhD, Naila worked in industry as an AI researcher at Qualcomm and later as a quantitative trader and quantitative strategist at Susquehanna International Group in Dublin. She holds a master's degree in data science from the Barcelona School of Economics and a double degree in mathematics and engineering physics from CEFIS UPC, with focus on areas such as game theory, artificial intelligence, financial mathematics, and cryptology. Yeah? So today she will give a talk entitled How Reinforcement Learning Agents Achieve Superhuman Level in Various Games and Origin Story. So in this talk she will guide us through some of the key ideas behind reinforcement learning agents that achieve superhuman level in chess, Go, and those. So please join me in welcoming Naila Sebastián Esandi.
Thank you very much. Hi everyone, welcome. Thank you very much, Mikkel, for having me. Today we're going to talk mainly about Go, but as Mikkel said, this can be extended to other games. We're going to go through most of the concepts of reinforcement learning, and we're going to use one of the most beautiful results that we have in the area to guide us through that. And do not hesitate to stop me if you want at any moment. If anything is not clear, ask questions. I'll be very happy to take them. I'll do my best. This work was done by the DeepMind group in London from Google DeepMind in 2016 and 2017, but still very relevant nowadays. We're going to start by presenting the game of Go. I don't know if anybody has played, but it's composed of this grid, and you have tokens, white or black, according to, for each player, and you have to place them on the grid. The exact rules are not going to matter too much for us, but what you need to know is that there is a way to win, and the way you win is if you conquer the most regions possible, like the greatest area. So has anybody heard of this before, and does anybody know who the best player in the world is? So it's now quite trending on Netflix, but he's called Lee Sedol. It's this man here. However, he was holding the title for many years, but he got defeated in March 2016 by AlphaGo, which is the AI we're going to talk about today. This was not expected at all because of the reasons we're going to see, and actually it was only expected to happen around nowadays, in a decade after what actually happened. And why was this so hard? So we need to understand why Go is hard. Let's compare it to chess. So chess was solved, let's say, quote unquote. An AI beat the best player in chess in 1997. It was Kasparov, and it just simply used brute force, like brute force algorithms where they just try to play all the possible strategies and see which one is better. However, we cannot do that with Go. Why? The branching factor in chess is 35. Branching factor means whenever you are in front of a board and there's a certain state in the board, how many different moves you can make. The average is 35. Then there is, on average, 80 moves per game in chess. And that makes the search space, so the possible different combinations, to be around the order of 10 to the 47. If we move to Go, the branching factor is already 250, and the moves per game are 150. That makes the search space completely huge and intractable, 10 to the power of 170. This is going to be a recurrent argument today to justify why we cannot do just brute force and why we need to apply all these different techniques to mitigate this problem. So the first thing we have to do is we have to learn. But what does learning mean? In AI, learning means the interaction between an agent and an environment. We have an agent that takes actions and perturbates the environment, and the environment itself, it feeds back a new state, so what happened after you executed this action, and a reward associated to this action. Well, to this new state, actually. See this, like this reward is very important. It's just a scalar term. So it's like if you received a grade from an exam, but they wouldn't tell you what went wrong and what went right. You just have the grade, and you have to take many, many exams in order to understand really how to improve that grade. Mathematically, we represent that as a Markov decision process, or MDP. And to define an MDP, we need a set of states. We need a set of actions that we can perform. Just think of Go, it's going to make it easier. We need a transition kernel that is representing the internal dynamics of the environment. So what happens when I execute action A in state S? Like, what's the probability of distribution of the next state? A reward function, obviously. We already talked about it a little bit. And a discount factor that is simply going to tell us how much we care about the present versus the future. Now, Go is the perfect example of this. Every legal board position could be considered a state, so that's our set of states. Every legal move is the set of actions. And the transition kernel could be simplified to something deterministic, because we know what's going to happen if the board is in a certain position and we place a token here. We know that the next state is just going to be the board plus that token. And the reward that we're going to define is 0 everywhere, except if we've won, that's going to be +1. And if we've lost, it's going to be -1. The discount factor is just going to help us with the math and make everything converge. But we don't really need to worry. It's not going to change our outcomes for this case. So, but we have all of this. We understand that we've modelized Go, but what really interests us here is finding a good policy. A policy is a rule that's going to tell us what to do on each state, which actions to take. If our opponent does this, what should we do? For us to understand what a good or a bad policy is, let's go at strong or a weak policy, this rule is usually stochastic, right? If you play deterministically in certain types of games, for example, rock, paper, scissors, if you always play scissors, you're super beatable. So, but in other games, anyway, you're gonna have something stochastic. In games more complicated than rock, paper, scissors, there's clearly actions that are better than others, that are gonna give you, make you win more times. So a strong policy would be one that really distinguishes which actions are better and picks them more often. And a weak policy would be a policy that does not really distinguish what's better. Don't get me wrong, this could be a very good policy if all the actions are equally good, but let's assume that not all actions are equally as good. So this is our goal. This is also AlphaGo's goal for playing Go. And let's see how they find a good pie. So first, before knowing how they find a good pie, we need to know how to evaluate policy in order to be able to classify which ones are good. For that, we're going to define the value function, which is just telling us if we're in state S and we follow pi forever, what's the expected reward? You can see here, it's the expected reward if we follow pi of the present reward, plus we apply the discount factor to the expected next state, plus we apply it twice to the state afterwards, and so on and so forth. This is going to tell us basically, like you understood, like this is, if we're here and we follow pi, what reward do we expect to take? Now, the other function, the Q function, is a little bit more restrictive, is if we're in this state and we take action A, we see what happens, but in the rest of the future, we follow pi. What is our expected reward? Super similar. If you don't really understand why Q matters, it's not really important today, but sometimes it helps us extract the optimal policy real quickly. But yeah, that's it. So now we have this, and we want to understand how to compute this value. And there's this beautiful equation that is the most important equation in reinforcement learning. It's called the Bellman equation. And it says that the value of where you are is equal to the value of the immediate reward. Sorry, the value of where you are is equal to the immediate reward plus the expected value of the future. And if you notice, this and this is the same function, just applied to different states, so it's recursive, and this gives very beautiful results. And every method we use for reinforcement learning is trying to solve this somehow. So let's see, one of the ways of solving it is policy iteration or value iteration. These two methods, they are dynamic programming methods. And to apply them, you need to be able to enumerate all the states and actions, and especially states, and you need to be able to compute, to know the dynamics of the world perfectly. If you don't know the kernel P that we talked about earlier, you cannot do anything here. You could estimate it, but yeah. Anyway, so let's look at these because they're going to be quite important, especially policy iteration. For the policy iteration, you take a policy pi and you evaluate it using a value function, and then you improve it using some greedy algorithm with respect to this value, and you repeat, you loop over and over until you find something stable, and until you find a fixed point, and you say this is the optimal strategy. For value iteration, you forget completely about the policy. You just use the value function. You iterate it using this Bellman optimality operator, which only means just take the action that will give me the best future reward. Like right now, take the action that's going to be the best for the future. And you loop this. This is a contracting operator, so it's going to have a fixed point. And once you find it, you extract V star. Sorry, we start a pi star from V star, so like the optimal policy from the optimal value function. But AlphaGo is going to focus, is going to use policy iteration. It's going to do, you have to remember this, evaluate, improve, because we're going to see it all the time. However, there was a problem. We cannot enumerate the states. We're going to talk about this all the time, just don't get too tired about it, sorry. So the first thing we're going to do is we're going to approximate pi using a neural network. And we're going to use policy gradient. We apply the method, which is policy gradient. This is for the improvement part of the policy iteration algorithm. And we're going to apply gradient descent on this neural network, parameterized by these parameters, theta. Theta is just going to be the whole set of parameters. So we have that the gradient of the expected returns is equal to the expected value of the gradient of these things. These are the returns. And this can be checked really quickly if you develop the gradient of the log. This is you're going to get a sum of gradients with things that are going to cancel out. But basically, we use this little trick because that is way easier to estimate than this whole thing. And this is the reinforced update. And this is what we're going to use for training all the policy networks. This is the way AlphaGo does it. So, but we're going to see it in a few slides. But yeah, for now, you're good. You have how the improvement goes. Now let's see how the evaluation goes. We already said that the search space was too big. We cannot look at every possible outcome. So when you cannot enumerate the states, what you do is you sample. I guess you have seen that in maybe stochastic gradient descent or things like that. I don't know. But anyway, this is what we do. When we have too many options and we cannot evaluate all of them, we pick a few ones at random and we see what the result is. There's two main methods in the literature. The first one is Monte Carlo. This one, you run a simulation until the end, and at the end, you see what the outcome is, and you update all the previous steps. And every time you count, you see the intermediate steps, you see how many times you've seen them in your different simulations, and you average the scores. And that's the value that you're going to give to all your intermediate states. But Monte Carlo, what it does is gets to the end and then updates. Temporal difference, or TD methods, we'll probably say TD methods when talking about this, is bootstraps at every single step. So we saw in the Bellman equation that we can use the next step's value function to update, define the current state's value function. So we use this idea to say, okay, we move on one step, we gain some information, and from that information, we also update the past that we've seen progressively. This is the idea behind Q-learning or even deep Q networks. And AlphaGo is going to use a little bit of both, but not quite. But it's good that you understand that these two methods exist. So again, before we get into what AlphaGo exactly does, there's one more thing. I'm sorry. It's still too big. Just picking actions, picking strategies at random is way too costly because you're wasting resources in doing things that could be really bad. Forget about Go for a second and just think about this paradigm. We have 3 possible actions, and imagine we have 3 buttons. We can press all 3 buttons. The first one, we've pressed it 50 times, and we've gotten a reward of 0.4 on average. The second one, we've played it 30 times, and our average reward was 0.6. The third one, we've only played it 3 times, but we got a 0.5 reward on average. Now, if we followed a random strategy, we would play whichever. We would be wasting resources on this one that we already saw is quite bad. If we picked a greedy one, we would be greedy with respect to the average reward. We'd be picking action 2 all the time, which is kind of we could be missing out on all the good things. So what we do is we apply upper confidence bounds, or UCB, which says let's be greedy, but against a certain type of function. This function is going to be the average plus a bonus term. And this bonus term is going to be bigger for the actions that we haven't explored enough and smaller for the actions that we know well enough. And this is interesting because this helps us learn in a smarter way and waste way less resources. So now we can put all of it together and we get Monte Carlo tree search. Now, games, they can be usually most of the time represented in trees. Each node represents a state. Each edge is the possible actions that you can take. And each node on the next level is going to be the next state of the board. So what we do is we're going to go exploring states by states, like conquering the tree. And at the beginning, we're going to use UCB. You might see sometimes UCT, that's just upper confidence bounds applied to trees, it's the name. So we're going to use UCB to walk down the tree and find what's the new node, new position of the board that we want to explore. Now we expand it. We add a new node. We say, okay, we're going to add this to our set of knowledge. And from then on, we run simulations to try to score it. This is called the rollout of the game. To try, okay, starting from this position, how many times do I win? How many times do I lose? And then at the end, you run a back propagation step, and you update all your previous nodes to understand which positions were good or bad. Because some position could seem very bad at the beginning, but then you find out that you can really corner your opponent onto very good strategies for you, even though at the beginning it seemed like it was meh, not really good. So the more you run this, the better your knowledge and the better your agent's going to be. And this was enough to beat an amateur player, but definitely not least at all. Definitely not a 9-dan professional, which is what he is. Like, it's like on Taekwondo and these sports, you get rankings, and like the highest you can get is the 9-dan. And that was still out of reach. Why? The random rollouts were too noisy, like these rollout policies, to find out whether the game was good or bad. And there was some handcrafted patterns at the beginning to try to explore down the tree. It didn't really have any good priors, so it was way too noisy also at the beginning. The solution that the DeepMind team found was to replace all these weak spots by neural networks, because they can learn for you, and they can do your job. So that's what they did. These are the 4 neural networks they're going to use, okay? Don't be scared. Like, we've seen all of this, so it's just going to be like restating the same thing, but with the right application. The first one, P sigma, is going to be a policy. These 3 are policy networks, and that one is a value network. This one's going to be a policy network that is going to learn from experts in order to be able to walk down the tree at the beginning. The third one, P row, is the improved policy. This is the policy that we're going to output. It's going to be an improvement of this one, of the first one, and it's actually what we're going to play against at the end of the learning phase. P pi is a rollout policy. So now we're not doing our rollouts randomly. We are not doing them like super great either, but we have a minimal policy that has a bit of an idea of what to do. We don't want a very good one, because then our rollouts would be super slow. So we take some fast, usually linear policy to walk us down the tree and to be able to run these games in a more intelligent way without wasting that many resources. If we and the last one is the value network, that's gonna predict the probability of winning given a state of the game, given a position in the board. And these networks, together with MCTS, Markov chain tree search that we just saw, and UCT, the upper confidence bounds, this is how AlphaGo was trained. So let's split this into blocks, but we've got it like this is the skeleton. Oops, sorry. Step 1, we're gonna train P sigma, the one that comes from that captures the knowledge from experts. So they took 30 million positions from KGS, which is a Go server online that has millions and millions of different games. And they just build a convolutional neural network. You probably have seen this for image treatment and things like that. That takes the input of the board and then predicts what an expert would do. What would the next step be? This is not reinforcement learning. This is just imitation learning. There is a right answer and an input and a right answer, or with certain probability. And that's what they do. They got 57% prediction rate. They said it was good enough, and then they continued. So we keep this. This is going to be our prior. Now, we want to improve the policy. And the way they did it is by self-play. They make the policy play against not itself, but a past version of itself. Because we're improving the policy with policy gradients, like we saw. And in order to know if certain moves are good or bad, the way to score them is via games against a random previous version of itself. Why is it random? Why don't we want to have the same one? Because obviously overfitting. You probably saw this plenty of times. We want to pick random opponents to be able to play against anyone. Yeah, that's it. So winning moves get given a higher weight, and losing moves get penalized. And that's how you do it. Then the fourth network, we're not going to look at P-pi, the rollout policy, because we already said we just want a simple thing. There's no training, there's no nothing. Just keep it as it is, because we want to keep it simple. But the value network has a little bit of interest. We use the self-play positions generated. So when we play against ourselves, we generate positions, and we see how many times we won or we lost. And we train this network, also a convolutional neural network, to predict what's the probability that our player wins given this state. Just making a regression on the outcomes. And remember policy iteration, we had the improvement bit and the evaluation bit. This is part of the evaluation bit. We have this and the rollouts, but this mainly would represent directly that. So putting it all together, we were selecting and using UCB to select, to explore the tree. For this, we're going to use P sigma. Then we're going to pick a new node. The new node that we pick is going to be expanded once by sigma, and then but by P sigma with the prior, and then we run the rollout policy. We use P pi to score it, but now we have a new tool. We can also use V theta, so like the value function. We use both of them. We will get some weighted average of those two scores, and that's the value that we will give to this new node. Also, like one of them can be slower than the other one, so one would be a proxy if we want to run iterations faster, or like, yeah, like these updates can happen like not simultaneously, but it's okay. Just think that these two are going to score our new node in position, and then we backpropagate it, and in the backpropagation, we are updating also the weights of our policy. So again, P sigma and upper confidence bounds are going to tell us where to look in the tree, where to explore. The value network and the rollout policy are going to help us score how good this new node is. This MCTS Markov chain tree search is going to put everything together, and the output is going to be P row, which is the improved policy. All of this has been generated through self-play. Don't forget that. Like, we're not playing against humans, we're playing against ourselves. The results? 4-1 against the best player in the world. Some people would be happy enough, but there's a very nice story here. When they were playing, you might have, I don't know if maybe this story is no, but sorry if you already knew it. In the second game, they played. So the first game, I'm pretty sure it was Lee Sedol who won. Second game, move 37 AlphaGo placed a token in a place that no human plays. So there's this thing where before move, I think 45 or something like that, you don't play within like a certain region of the board. You stick to the outside. And AlphaGo played inside that region, and everyone thought it was a bug. Everybody was very confused. Was like, okay, like, it's just the AI doesn't work. But it turns out at the end of the game, it was the key to like put everything together for AlphaGo to win that game, to finalize its strategy. So what we're actually seeing is AI, only within a few hours or days of training, generating new knowledge that on a discipline that humans had been studying for like 2,500 years, which is quite, I don't know, for me it's like really cool. So the next question, so this is done, this was AlphaGo. Now the DeepMind team asked a even more challenging question. Seeing that AlphaGo is doing better than humans, what if we remove the human data entirely? So the next paper they published was a new version of AlphaGo. It's called AlphaGo 0 because it has 0 human knowledge. It's what we call tabula rasa, which means, well, you might have seen that in, I think it was philosophy in second year of bachiller. I don't know. You start with absolutely nothing and you build from that. So we got rid of most things. We got rid of the human expert games. There's no prior from humans. There's no rollout policy also, because they decided they wanted to simplify the model. There's no 4 separate networks. We're just going to have 1. And there are no handcrafted features, because sometimes, like for some things, for the exploration phase and stuff, they added some things manually from the knowledge of Go. They also got rid of that. And they only kept Markov chain tree search, and the self-play, and this one network. So already this is conceptually much simpler than what we already saw. If you survive to all the rest of the talk, like this is going to be much simpler. So this is the only network that we're going to have. It's going to be a ResNet, a residual net, which are these networks where you have the input, you process it, and then you add it back at the end. So it receives the board just as it is, as a raw input, interprets it, and it outputs the policy and the value into different heads. What does this make? This is complete shared knowledge between the value and the policy. Usually, you might have heard of actor-critic models. There's usually two networks or two, let's say, entities or agents. There's one that's going to be the actor, one is going to be the critic. The actor takes actions, and the critic evaluates those actions and feeds back to the actor, like, what did I think of what you did? In order to improve itself, like they just improve each other. This thing is done all in one network, because if we backpropagate from the value head, we go back to the shared nodes with the policy head. And the same thing, any backpropagation shares information with the other head. So we have one single network that acts as an actor-critic model and is much, much simpler than what we had before. Now, how do we train this? We have our network that outputs what we're going to call the priors, pi and v. Now, we're not going to have any role policies, so the only way we have to score our policies is by self-play or this value function. So we feed that into MCTS. This simulates many, many games, producing a stronger pi and getting the results of the games. And that feeds back into the neural network, which itself tries to fit the old pi hat, to the improved one, so via gradient descent, like we saw. And the v, so the outcome, the value function tries to regress it on the outcomes. So the value function wants to predict the outcomes, the policy just wants to mimic the improved policy. This is all the equations that they have, that we need. They probably have more, but this is all we need. This is the loss function for the improvement of this network. We want to regress the value function with respect to the outcomes. We want a cross-entropy loss to make pi closer to pi hat. And we want a regularization term that simply is going to avoid it's going to prevent our parameters from exploding. You might have seen that in, ridge and lasso regressions. So yeah, there's only these three terms. It's quite easy, and you compute a gradient on this, and you update the network, and you're good. The results were, let's look at the figure on the left. This comes from the paper. The green line was AlphaGo Lee, which is the version of AlphaGo that beat Lee Sedol. The blue line horizontal here was the best AlphaGo model that they had so far at the moment. And the blue curve is the AlphaGo 0 model. And these are the number of training days. So within 4 days, it had already beat the version that beat Lee Sedol. Within 30 days-ish, it was at the same level as the best one, as the best AI that was using human expert data. And then at 40 days, it was clearly superior to any other version that was using human intelligence. This was clearly very impressive. But there's a little story here as well. If you look here, there's AlphaGo Lee, which is around 3,600 ELO or 3,700. And there's AlphaGo Fan. This Fan is Fan Hui. is a Chinese player who moved to Europe when he was young, and he was the European champion of Go at the time. The funny part is that when he lost against AlphaGo fan, instead of just being sad or wherever, going to a corner, he decided, well, if you cannot beat them, just join them. And he joined the DeepMind group at Google London. So yeah, he helped develop the newer versions of AlphaGo. So that's it. We're done. Richard Sutton is is one of the writers of one of the biggest books in reinforcement learning, which basically explains everything there is to know. Like all the basics are there. If you ever need it, it's a good source. And he called this the bitter lesson, which is when you leave the machines alone, you don't add any bias from humans, and they do better than us. This is exactly what this has taught us. Machines were doing better without us, but I don't want to extrapolate this to other domains. Just let's stick with Go. So let's wrap up what we've seen today. Like, it was a lot, but we went from Markov decision processes, MDPs, to model the world, to realizing that what we need is to extract a policy, to know which is the best one. We need to evaluate it with a value function. The way to compute the value function is the Bellman equation, and the way to solve the Bellman equation is the policy or value iteration. This is all the theory. Now we look at the reality. The reality is that this is too big, we cannot deal with it. So we start approximating policy gradient for the improvement of the policies, Monte Carlo and TD learning for the sampling, bandits or upper confidence bounds for a more intelligent sampling, and MCTS to put everything together and model the actual game. Finally, the actor-critic methods and self-play for the machine to teach itself. This isn't it might seem like separate topics, but I hope I've been able to convince you that they're all related and they're just iterations of the same thing with different solutions. So let's see. Now it's all done. We're going to see where the field has gone ever since, because this was almost 10 years ago. 1 year later, they published AlphaZero. It was the same algorithm, same ideas, just they gave them the rules of shogi or chess instead of just Go. And they proved that this is just the same algorithm works for all three of them. Shogi is a Japanese version of chess. That's all I know about it, so please don't ask me any more questions. Then in 2019, they published MuZero, which learns the model, learns the rules as well, via the reward. So you use the reward to infer what's legal and what is not. In 2021, the same team published AlphaFold 2. This might seem like a bit of a stretch to go to such a different domain, but it's about protein structure. And it really made very big advances in biotechnology, because proteins are chains of amino acids and they can form different shapes. And the search space, there's so many amino acids, so many possible combinations that the search space is insanely huge. And thanks to algorithms like this, they've been able to understand and even generate new forms of proteins. So this was really big for anyone doing any type of biotechnology or applications like that. And finally, in 2022, we have RLHF. I think you saw a little bit about this last week, if I'm not wrong, reinforcement learning with human feedback. It's used in LLMs, and you do the same policy gradient we saw, except that the rewards are learned and they're given by humans, basically. You know, when in one of these LLMs, I'm not going to say any names, you have an upwards button or a downwards to say if the reply was good, or even when you reply to it and you say, oh, this was really bad. This is human feedback that is helping train the models. So all of it was the same template, with neural networks, search, and self-play. With these three ingredients, we were able to solve all of these problems. And way more than, the story started with Go, but we've seen that it's way, way bigger than just Go. It was just a way to take a problem that seems very complicated, but that can be divided into smaller blocks that we can actually conquer. And yeah, and then let's go one step farther. What we don't have any information whatsoever about the game. AlphaGo had human data, had the rules of Go, and had a reward. AlphaGo 0 got rid of the human data, still kept the rules of Go and the reward. And also like Alpha 0 with the chess and shogi had the rules of the game. Mu 0 had no human data and no rules, but had the reward and could infer the rules from the reward. Zero-shot reinforcement learning, which is surprise what I do, has no human data, no rules, and no task or no reward. So what we do is we pre-train agents without having any idea of what the task is going to be. So like a reward can define a task, right? Because a reward tells, like a task is, the goal of a task is to reap the highest reward. So we don't know what problem we're going to solve, and we don't have any rules or anything, and we don't have any feedback during learning. So what we do is we let the agent explore the environment during learning, and then at test time, we are given a task, and we have to solve it immediately. We're not allowed for any fine-tuning, we're not allowed for any further learning, nothing, just like very quickly. Some people just say, okay, you can do some linear computations and stuff, because obviously something you have to do, but there's no learning allowed at all. This is a way of thinking about this is, imagine we have a model that can be trained in a supercomputer, and then we have to deploy it in a small device. And this device is going to have to solve many different tasks. Imagine a self-driven car. It's going to have to take you to anywhere you tell it. You're not going to know when you're training the model where this person is going to want to go and how the state of the streets are going to be on a certain day, like if the red lights are going to be red or green, or like there's going to be kids crossing and playing behind a ball. So the agent, like the deployed agent, is not allowed for compute time, but it is required to generalize to any given task. So it's quite challenging, but it's gaining a lot of attention these last few years, sorry. And some of the references are Toiti and Olivier. They wrote a bunch of papers that what they're doing is they're encoding, they're using encoders, decoders to try to solve this. But we're not going to get into this anyways. This is not the topic of today. If you have any questions, I'll be happy to take them. But the questions can be about anything, not just my research. And if you want to read anything more about this, the Sutton and Bartow book that I mentioned earlier is like really good. It's really easy. If you ever have a question about reinforcement learning, go to that book first, because the theory is there and it's very clear. Then David Silver, who is the writer of these two papers that I just presented, has also like some lecture series on YouTube that could be useful. Finally, these two papers, I think you've already read them, but they're quite easy to read. Like, maybe you won't understand all the details, but it's not hard. Like, you have like very deep maths and you have to stick into like on an equation for like 30 minutes before you understand it. It's really, Google usually writes like very readable papers. Then you finish them and you realize you have understood nothing some of the times, but it's okay. So thank you very much. That was all. I'd be happy to take any questions.
Hi. My question is about mu0.
Yes.
Because you said that it learns the rules with the rewards.
Yes.
But like, what is the reward of doing a forbidden move? Like, is it like you just lose, or you assign like really negative value?
I haven't read the paper, but I would say like what we usually do is assign a very negative reward that is much, much bigger than the reward assigned to winning or losing, so that the agent completely avoids taking this action.
Okay.
Like no matter, you know, the UCB algorithm, there is this bonus term. No, like this bonus term is never going to be big enough to counteract this, this really negative reward.
Thank you.
No worries.
Okay, and my question is about the last algorithm that you presented or that you mentioned, and is that without a reward, how does the model or the agent understand which is its purpose?
Oh, about zero-shot
Yeah,
reinforcement
zero-shot.
learning. So it doesn't really, it only understands what its purpose is at test time. The way we do it is we try to encode some function that, given a reward, will tell you directly what the optimal policy is. So instead of learning how to move around, it learns how to react to different rewards. Does that make sense?
Yeah.
It, mathematically, what we do is, so you all understand policies and how policies work. It's just the rules of what to do. Have you ever seen convex optimization problems where you have like the primal and the dual problem, and you have like dual variables? You can find that there's a way of transforming these policies into one thing that's called occupancy measures, which are going to tell you, on average, how much time you're going to spend on each state. The occupancy measure of a policy pi is going to tell you that, like how much time you're spending on each state. So if you have a reward function defined on the states, you simply do the dot product between those two elements, and you already have what's the expected reward. So using these sort of ideas and keeping like a bunch of them in like smartly picked, you pick smartly which ones you're gonna do, which is what I'm trying to figure out how to do. You are able to approximate the optimal policy very, like you are able to extract a policy, to select one of the policies you've saved, and you want it to be very, very close to the optimal policy. So it changes a bit the problem, the type of problem. It's a problem of reacting to a reward instead of a problem of solving this control problem. But yeah, just taking the dual makes things super simple, and it makes you able to solve these things.
Thank you.
Hi, talking specifically about the AlphaZero, I read in the paper that AlphaZero, like specifically in Go, like it beat, I think it was 61% of the times the AlphaGo Zero. And what do you think is the main reason for that? Because, like, if you think intuitively, it's like using a generalized framework, like for the same one for the chess and the shogi and whatever. If you think about it, it should like work better the one with specialized for Go. And why do you think is better the generalized one?
I don't have the right answer for this, but I'll give you my intuition. The same way we removed the human data and it generalized better, the learning of more generalizable strategies, like having a model that's more generalizable, sometimes gives you better intuition for games for one of the specific games. Like you can use, obviously we don't really know how the weights are updated in the middle, but for me it's imagine a kid that knows how to play the violin, the piano, and the flute, and now it learns how to play the guitar. Or like, versus a kid that has only played the guitar and starts from scratch, probably like it can infer knowledge from the other disciplines. That's my intuition, but I am not sure if it's the right answer.
Thank you.
Hi. I was wondering, because you talked about in AlphaGo that the way it won, it was because it did like a weird move that normally no one does, and then it won because of that. So has there been like studies done to understand how they work, like how these moves then work and these strategies that the neural networks come up with?
Yes, there is So first of all, only in game 2, they played 5 games. Only there was a weird move only in that on that second game for that specific tournament. But then I guess they've played more times against it. So in chess, professional players usually train themselves against AIs because they know they're going to teach them moves that other players wouldn't. It's the same thing with Go. They have analyzed the moves and they have realized that there exist policies, like strategies, that will make these good moves good. So what they do is the opposite. It's like inferring from playing against these AIs or like watching them playing against each other. They learn new moves and like humans are like seeing, oh, why is this move good? We had never really thought about it. Because it's what I was trying to explain earlier. A move might seem bad at the beginning, but then if you go down the tree, you actually have a good strategy to push your opponent into a corner, like figuratively. So that's the thing, when there's too many steps between the move, like the weird move, and the actual reward that comes back, you probably need like some AI to keep track of all of this. And then a posteriori, the humans can look into it. Thank you.
Hi, my question is more philosophical. Like we've seen that these AIs beat humans, but do you think that when a game gets more complex, like for example an online game or something like that, which has many variables, do you think the gap between the AI and the humans gets narrower, or do you think it's a matter of time and resources that they catch up, or even if they are already catching up?
I think AI is going to be way better than humans. Like the more complicated the problem, the more, the stronger a neural network is, because like it has no, and it's not no limits, but compared to humans, it has no limits about how many things it can be thinking about at the same time, how many things it can be controlling at the same time. So actually, I would say the opposite. Like the more complicated the game, potentially the better the AI is.
Similar to the last question, I want to know which are the games that the last model, the zero shot, is being trained, like still the Go and Shogi and chess, or new games more complex.
We're not actually looking into games. It's mostly used, like it's a developing area, and I work on the theoretical part. I do maths, but what the applied papers that I read are mostly robotics, and they want to solve like they want let's say multi-purpose robots, and they put them in an environment. And mainly what they're doing is it's mostly with simulations, and they try this. I don't know what it's called. It's called something like zoo something, and you have like a half cheetah, and you have like some sort of humanoid version, and they're all like online, and like they learn how to move. It's like simulated robots, and we're still there. We're not in the real world yet. And what I do is try to see how good these models could be, like how bad they could be. What's the guarantees that we could put like we could have with them? But no, it's not with games yet. Sorry to disappoint.
I had a question about AlphaFold, although it's a bit different from these models that we discussed. In those, we had the three options: we either win, draw, or we lose. In AlphaFold, because it's a protein problem, what is the actual feedback that the model is getting to know what it is looking for?
I do not know, but probably something like the protein has already been detected elsewhere or something like that. But I don't really know. I'm sorry. I will look into it. I can look into it and get back to you if you want.
Hello, I have a question because we have seen that AlphaGo beat humans, then AlphaGo Zero beat the previous one. In the first case, we have seen that it is because we removed the human data, so we got that human bias out of the equation. Then when we got more general, we could say that there is like Go bias that got out of the equation because it got more general with other games. So do you think that even if we have a very good model with this kind of models that we are seeing, if we compare it with the absolute hypothetical perfect model that sees all the probabilities, do you think that we are going to get to the point where we find no bias and we get close to that perfect model, or with this approach we are always getting to find a new bias?
The bias was initially introduced by human data, but so it all depends on these gradient descent methods, right? If we understand that the Bellman equation is a contraction, it means that, and we assume, like in theory, if we solve this with dynamic programming, we would get to the perfect state. There would be absolutely no bias. The problem comes from all these approximations. All these neural networks, they're actually approximations of the real policy function and value function, like the true policy and the true value function enumerated on each one of the states. So yes, there is always going to be a bias, but it's not necessarily induced by priors from humans or from actually AI. It comes from the parameterization. However, if we allowed for infinitely big functions, parameterized, like functions with infinite parameters, and if we allowed compute to be infinite, then yes, we would get a perfect score. But that is just intractable. It's like when you have a Taylor expansion, if you allow for infinite terms and it's a non-polynomial function, continuous function that you're trying to approximate, if you allow for infinite terms, you're going to get the perfect approximation. If you only allow for a limited amount of ones, which should be the equivalent of having a limited amount of parameters, you're not going to get the perfect. But you can bound the error. Has this replied to your question? Thank you very much.
Okay, so the motivation in the past for training these models was beating the humans players. No?
I'd say.
But now that the gap is so big between humans and AI, what's the motivation for training a little better AI model playing Go?
The answer is simple. It's just creating knowledge. The AI is creating knowledge that we haven't been able to do in a very long time. We probably would be able if nature gave us 40,000 more years, but if we can have it within 1 month or 2, if we are training AI, why not take that? So mainly that's what's happening right now with AI. We're not really using it to beat humans. We're using it, well, yeah, I don't know if they're using to that, but the way I understand it is we're using it to generate more knowledge at a faster pace than what we would be able to.
In the models like AlphaZero, AlphaGo, and this type of things, what do you think is the most difficult part of programming that and this type of things? What do you think they spend most time in the progress?
I have no idea, but I would say mostly when you have these sort of problems, the biggest challenge is encoding the input, and because then if you have to do a 13-layer convolution network, you've already done thousands of it, or your team has done plenty of them, so you just have to copy paste one. So actually capturing the specifics of the game, the specifics of the input, and the specifics of the output, I would say that's what they spend the most time. If we don't count the training time, obviously, because that's just going to be running forever. But yeah, that's the biggest thing.
about creating knowledge. I don't know if you are familiar with Alpha Evolve. It's a no. Okay,
Sorry.
I
You can
just
tell me what it is.
it's like a model of the Alpha series that works like a superpower researcher. Like, and I think it was released the past year. I just found it yesterday, so I don't know too much about this. But yes, my question was if you knew about it and if you could talk about it. But
Oh, I'm
it's
sorry.
okay. Thank you.
Thank you so much, though.
I have a few questions more to finish. So maybe the first one is, can we play against AlphaGo or something like that? Is there?
I think so.
Yeah.
I think so.
Okay.
I don't know where it is, but
Okay. And then, do you know something about the hardware you need to train this? I mean, I know there were in the paper, but there was a question before in class uh, about the amount of computation you need to learn this Alpha Zero or whatever, compared, for example, with training a ChatGPT model. I thought it was much less, but
it's
do you
way
know?
less. No, of course, because just look at the input, at the amount of input that you put into it. ChatGPT took, I don't know, like a very, very long time. And this could be done without putting actual servers under the sea or anything. Like this was 10 years ago. Everything was calm then. So yeah, no, I would say there's no point in comparison between like the possible states of a Go board versus the actual amount of knowledge there is in the internet. But I don't have a like
No,
quantitative
fine.
answer for you. Sorry.
Okay, and then for me the last question will be, okay, so you have been working in Qualcomm, in Dublin, in another company, so in several companies before doing or starting the PhD. So can you tell us a little bit about your journey? Why have you finished doing the PhD? Or yeah, a little bit about life.
Okay. So I don't know if I want this to be recorded. Can we cut this out? So so the story is I went to Barcelona to do my undergrad. I did maths and engineering physics in this program that allows you to do both at the same time at UPC. And we cannot, due to the nature of the program, we cannot do an Erasmus. We cannot go on Erasmus. But instead, what we do is we go abroad for the bachelor's thesis for the TFG. And we do it, we have a mobility program, like internal one. And I went to the US and I was working on game theory. And I really wanted to do a PhD back then. But I didn't like it there. I didn't like, I was very homesick and I wanted to come back to Europe. It was also in an economics lab, even though I really liked my program, the problem I solved. I wasn't really convinced to spend like actually 5 years there. So I came back. And that's when I went into Qualcomm and I worked for 6 months there. And the last of which overlapped with my master's. And I really liked Qualcomm. I left it because it was completely remote, and I'm a very sociable person, so I need to be around people. At the beginning of my master's, I got the position in Dublin. And it was a bit of an impulse from like the lack of in-person things in Qualcomm and the fact that my friends were in Dublin. They had this this amazing office, everything. I went to visit them. Everything seemed super cool. So I went through the hiring process. I got the job. I was like, okay, like it's also like trading is such an opaque industry. You don't really know what's happening until you're in there. So I had curiosity. And during my master's, I found out. So one of the reasons I didn't go straight to a PhD is because I only knew from people that were doing it in the US. Most people from my program, from TEFIS, would go to the US to do a PhD. So when I came back to Europe, I understood how PhDs work in Europe and stuff. And towards the end of the year, I was actually talking to my professors at UPF, at the PSC, about doing a PhD there, but I already had the contract, so I went to Dublin. Like, I give this a try. And I gave it a try until it wasn't for me. And then I came back and decided to do a PhD. It was sort of in the plan all the time, but I allowed myself to explore other things in the meantime. And yeah.
Will you start the PhD again?
When?
Will you start the PhD again?
I've only been doing it for like over a year. But yes, no, I'm really, really enjoying the PhD life. It's super chill compared to quantitative trading. Like working between 10 and 12 hours a day with no lunch break versus getting to work whenever you want, leaving whenever you want, putting the amount of effort that you want. The first day you get there, the professor tells you, like, this is your thesis. The work that you put on it, like the more work you put in it, the better it's going to be, but nobody's going to be, like you're an adult, nobody's going to be behind you trying to put pressure on you. And it's very nice. I think I've been very lucky with the group that I found, where I ended up. Everyone's very friendly, we support each other a lot, and we work in different topics, so there's not too much competition. It's more like collaboration. They're like tangent topics, so it avoids any friction or anything. So yeah, we do a lot of activities, and honestly, I like it. It's a good life for me. It's not for everybody, but yeah, I was also lucky enough to be able to handpick my topic.
Mm-hmm.
I actually started saying I'm going to do something else, and then just found out that I didn't like that. Heard about this, started reading about it, talked to my supervisor, and now it's been a year that I've been working on this. So.
Okay.
Yeah, thank you very much.
So, there are no more questions. Please, thank you.
Thank you very much.